Okay, let's get started. Welcome to Oceanography, week 7. This week we'll be talking about ocean circulation. And we're gonna have a brief lecture, try to hold it to under 15 and 20 minutes or so. And then, as I said last week, we will separate into the breakout groups, the breakout rooms, and each of the teams will have a chance to go over their submissions for milestone 2. Very important milestone because that's what establishes your research base on which each of the teams are going to be developing their term research project. And we want to make sure that everybody's off to a good start. And also, as I emphasized last week, that you're taking the principles of oceanography, and that's the name of this class, taking the principles of oceanography that we're reading about, that we're talking about in our lectures, that you're thinking about, and trying to translate those somewhat textbook kind of concepts into real world examples that you're reporting on for your research project. So we really want to emphasize that that's one of the essential components of doing this research and of combining it with the readings and the understanding that we're getting of these basic principles and concepts. Okay, so we talked last week about circulation in the atmosphere, and we looked at the ways in which the uneven heating of the Earth produces pressure gradients and movement of air and convection cells, and that there are a series of convection cells that are most intense at the equator and consist and then go in pairs up to the poles, the north and south high latitudes. And then we also looked at the way in which these movements of air are influenced by the Coriolis effect, so that in the northern hemisphere, any wind pattern or any wind current is being deflected rightward. That would be, and in the southern hemisphere, any flow is deflected to the left. And so if there's a flow of air along the surface, across the surface, and in the Hadley cells, Coriolis effects deflect that westward. So there's a westward intensification of winds around the tropics. Those winds were called the trade winds because they facilitated trade between Europe and the American continents back in the days of sailing ships. And those surface winds, as we'll learn this week, also set in motion the movement of ocean water. And they create irregularities in the surface of the ocean, which translate into ocean currents. So we'll be thinking about ocean currents in our lecture today. And we'll be looking at ocean currents in the surface of the ocean, and then also movement of water at greater depths. Of course, the surface of the ocean is only a tiny fraction, less than 10% of the total ocean volume. And all of the ocean is in motion one way or another. And those motions are determined by, principally by the wind in the surface, but then by density differences in the deeper regions of the ocean. Okay. So the key concepts that we're going to be covering in this chapter are that ocean water circulates in currents. And so we think about currents. A lot of the currents that we probably experienced are tidal currents, but there are other currents that move water. And these currents are consistent enough so that they have names and generalized features. And you've all heard of the Gulf Stream, which is an important current, but there are many other currents, the Hiroshima current, the Humboldt current. There are many currents that have different names, and they are created by the same sorts of forces, predictable forces, as create the winds. The upper 10% of the ocean, wind drag caused most of the ocean and most of the motion, most of the direction of water movement. And then the Coriolis effect deflects that motion. The deflection is most pronounced in the higher latitudes. So the Coriolis effect increases with increasing latitude and decreases with decreasing latitude. So at 0 degrees latitude, that's the equator, the Coriolis effect is also 0. And at 90 degrees, at the very North Pole or the very South Pole, the Coriolis effect is also 0. But as soon as you start moving away from the poles, the Coriolis effect is induced. The ocean surface, and this is very important, is not perfectly level. We talk about sea level, and we think of it as, flat as a pool table or something like that. But in fact, if we look at the surface of the ocean over large distance scales, it turns out that there are variations in the height of the ocean height. And these variations are caused by a variety of effects. The wind causes a bulge of water to sit in the western portions of the ocean basins. And there are also sort of temporary temperature-induced bulges. And there are also valleys. So there are high points, high places in the ocean, and low places in the ocean. And anytime there's a surface, an inclined surface, gravity is going to set water in motion to try to obviate that gradient. And so as soon as the water is set in motion, by gravity, the Coriolis effect takes place. Okay, and so we're going to look at that process. So, and in the lower 90% of the water, the midwater and the deep water, circulation is driven by pressure differences, and high pressure trending towards low pressure. And again, the Coriolis effect is going to deflect flows, density-driven flows along the contours of pressure. So we're going to be looking at the Coriolis and ocean motion in greater detail this week. But an important concept that we'll be dealing with is the idea of vectors. So increasingly, as we've been reading the text, particularly in chapters 8 and 7, you're starting to see movements of water, movements of air represented by arrows. These arrows are vectors. I'm almost certain to run across vectors in your education to date, but we're just reviewing what vectors are. So vectors are a very convenient way of expressing acceleration in multiple directions. So if we think about this student jumping off a wall, at any motion, so we kind of know what he's going to do. He jumps up and he's going to go down and land somewhere out here. Well, at any point in his trajectory, at any point in his leap, he's accelerating. He's got accelerations in different directions. If we ignore the acceleration into and out of the page, there's an acceleration in this direction from the left to the right caused by when he jumps. And jumps up and jumps out. So that acceleration in the x direction is represented by this acceleration x, ax. He's also accelerating at every moment due to gravity. The acceleration of gravity is constant. So the initial acceleration is caused entirely by the propulsive force of him leaping off of this wall. But that acceleration decays, as a result of friction, and so he stops accelerating. His acceleration decreases in that direction along this. But this acceleration of gravity is constant, so eventually it'll come to rest on the ground at some distance out. Well, a vector of his motion, a vector of both accelerations from his starting place, is represented by a single arrow that combines the x acceleration and the falling acceleration, the acceleration in z, this arrow. So this is a vector of his total accelerations. And this is a good way of representing motion. It's very intuitive. You can look at these arrows and you can get a good firm grasp of an accurate grasp of what's happening. Vectors can be expressed either as translations, the degree of motion in one or more of the directions, or we can use radial notation to look at the radius and the angle of deflection. So we can represent vectors as either sums of direction or single directions at an angle. So, and it turns out that we can add vectors. So if we want to know what the total distance is, so if we look at this acceleration here, the first initial acceleration was in this direction, and the secondary acceleration in this direction. If we want to know the total acceleration of both of these, we add together a plus b and x. Okay? And so we can sum up over multiple directions. Oops, I missed out a slide here. So if we think about, somebody who walks east for 1 kilometer, then she walks at 30 degrees true for 2 kilometers, west for 2 kilometers, and then southwest for 2 kilometers. Where does she end up? So we could look at all these distances. So she ends up a negative 4 kilometers north and a negative 7 kilometers east of the start, which is the same as 0.4s and 0.7 east. So how far did she travel? Well, here we can apply our friend the Pythagorean theorem, and we add up the sides of the triangles, 0.4 squared plus 0.7 squared, and take the square root of that, and we find out that her total travel was, the total distance, total length of that arrow was 0.8 kilometers. So you can add up positives and negatives and end up with a consistent answer. So this is a good way of adding that. And so we've talked about motion accelerations in the X and Y directions, but of course in the ocean we have a third dimension, that's the Z dimension. So AX, AY, and AZ are all vectors, and the same principles apply. We can look at changes in acceleration over time, and they all have to sum up to a single vector. So this notion, so you see these arrows and the lengths of these arrows representing different motions. These have actual real-world mathematical foundations, and these foundations help us understand what the net effect of any acceleration is going to be. All right, why am I beating on this horse? Because in the ocean, we're looking at accelerations that are due to gravity and also to the deflection of Coriolis. So here is an equation representing the Coriolis effect. Coriolis effect is represented by omega here. And so the direction in time is equal to the effects of Coriolis, so the motion, the pressure. So this is pressure, and then the Coriolis effect. And the Coriolis effect is proportional to the sine of theta, and the sine of theta in this case is the sine of the latitude. So the sine of latitude 0 is 0 at the equator and 1 at 90 degrees at the poles, plus gravity and plus all their forces. Well, all of the other factors in this equation drop out. Gravity is constant and everything is constant. So motion in the ocean is due entirely to gradients of pressure and the response of acceleration due to that differences in pressure as influenced by the Coriolis effect. So pressure moves water because of the influence of gravity. So, we've been talking about the Coriolis force, and it technically is not a force, and I'd be remiss if I called it a force, because physical oceanographers get very fussy about that sort of thing. It doesn't really do any work, but it's just an apparent deflection that we notice because we're living on this sphere. And if you recall, when you looked at that cartoon that I showed of the cannonballs and the arrows, that when you backed off and you were no longer in the Earth's reference plane, these motions, these deflections of Coriolis disappeared. So, but they're real in the world in the sense that they change the direction of motion for all objects traveling across this rotating sphere. Now, the accelerations due to the Coriolis and the pressure effects are very small. So if we take the value of theta, of omega as 7.3 times 10 to the minus fifth. And this has to do with the speed of rotation of the planet. And we consider 2 times the acceleration times the sine of latitude at the pole, where the Coriolis effect is greatest. We have about 1.5 times 10 to the minus 4 meters per second at the pole. And this at 45 degrees, this drops off to it's 1.5, 1, and then 0 at the equator. So these are teeny tiny accelerations, but over time they add up. And when we consider the huge volumes of water that are in motion of the ocean, these tiny accelerations and these tiny deflections are important. So there are little tiny arrows added to the overall forcing factors. But those little tiny arrows, those little tiny accelerations due to the Coriolis effect have a huge influence across oceanic scales. And it should be emphasized that in the ocean and in the atmosphere, friction is certainly plays a factor. But in the open ocean, there's relatively little friction effects, and so we can ignore friction and simply consider the pressure gradients which are driving that. Okay, so that's a look at this. This is laid out in the textbook, and you can certainly read over that if you need more discussion of the formal understanding of what the Coriolis effect. But now let's briefly focus on how this is going to drive processes in the world, and then I want to talk about gyres and mounds in the ocean, and then something called the Ekman spiral, which should be familiar to you from your readings in Garrison. So, as we talked about in the last chapter, looking at oceanic circulation, we have this series of convection cells, the Hadley cells, the Ferrel cells, and the polar cells. And the effect of the rising of air, the heating of the Earth and the ocean across the equator causes this low pressure zone. Air rises and air rushes in across the surface to replace that air which rises as it warms. Okay? And so in Hadley cells, there's a north to south movement of air. And in the Hadley cells in the southern hemisphere, there's a south to north movement of air to replace the air which is rising around the equator, the ITCZ, Intertropical Convergence Zone. Okay, well, again, these arrows are greatly exaggerated to show the difference here, but the overall effect is this sort of westward drift of the wind. So there's and you think about it, the pole, the Earth is rotating in this direction, and you can see how the Coriolis effect is causing the deflection to be essentially opposite to the direction of rotation. Joseph, you have a question?
Yeah, so like in the Hadley cell, is the westward motion like stronger the further south you go towards the equator, or is it the same for the whole cell?
No, the westward deflection decreases as you get closer and closer to the equator. So this is really exaggerated, but overall, this westward deflection, this westward motion is really important. And this is something what's called west wind drift. And so this general acceleration towards the west in the planet, whether it's the west in the southern hemisphere or the west in the northern hemisphere, moves huge amounts of air and water. So I've been talking about the wind here. That's what these cells are depicting. But that wind blows across the surface of the ocean, and the friction of the wind across the surface of the ocean sets the water in motion. And this effect, called west wind drift, is responsible for moving, a lot, in aggregate. It's the largest surface motion of water. There are also more localized currents like the Gulf Stream, the Canary Current, etc. But the major motion of water in the surface oceans is due to the west wind drift in the temperate zones. Okay. All right. So, imagine that there's this sort of steady pressure of the wind on the surface of the ocean, sort of forcing water from east to west. And the result of that is that there is a mound of water that builds up in the western side of ocean basins. And it doesn't matter whether the ocean basin is in the northern hemisphere or the southern hemisphere, because of what we've learned about the Coriolis, deflection to the right in the northern hemisphere, deflection to the left in the southern hemisphere. That net effect is a movement to the west of wind and water, westward drift. And so there are gyres in the western side of all of the major ocean basins. And these gyres are these essentially large mounds of water. Now, when I say mounds or hills, that's a very qualified description, because the actual difference in height is measured in a few centimeters. 10 centimeters, 20, 30 centimeters difference across hundreds of kilometers of ocean surface. So, it's a very slight topographic high or barotropic high, but it's significant. It represents a huge amount of water, and the tendency of gravity to accelerate water across those gradients is also going to then start water moving. Okay, so you get this picture then of water being displaced to the center. So here we are depicting the northern Atlantic Ocean, and so here's the equator, and here is the the wind. The Hadley cells are displacing, accelerating wind to the west, and so there's this center depicted to offset to the western side of the North Atlantic. Okay, so there's this mound of water. Again, the mound is hugely exaggerated here relative to the lateral directions, but this is significant. So any water or any parcel of water within this mound is going to want to accelerate, fall from the high point to the low point. So water within this gyre is constantly accelerating. Well, as soon as it accelerates, what happens? It's going to be deflected, right? So it's trying to fall, to accelerate from the high of this gyre toward the lower portions. So there's an acceleration down across these gradients. Well, any motion, in that direction is going to get deflected, right? So if you're moving from this, roughly circular mound or subcircular mound, maybe it's more elliptical, and sort of falling outward from that, the acceleration to the right is going to produce a clockwise motion. Right? So gyres, you've probably heard the term gyre, is referring to a big rotating mass. So the general acceleration of the gyre is a rotation in a clockwise direction around this high point in the ocean. And so these gyres, ocean gyres, are a component of all of the ocean basins, and they typically, well, they always occur on the western side of ocean basins. So there's a gyre in the Western Atlantic Ocean, a North Atlantic Ocean, and there's a gyre in the Western South Atlantic Ocean. In the western side of the Pacific, there's a gyre, etc. And the position of the continents creates other forces, which we'll talk about in subsequent discussions. But this major concept of having a gyre and rotating water, because the acceleration to try to offset this gradient, and then the Coriolis effect inducing this clockwise motion around the high point. Okay. All right, so that's a sort of a generalized motion for flow within a gyre. And gyres are these large-scale features in all of the ocean basins. Looking at it in a somewhat smaller scale, we can think about any time that water is set in motion in the surface ocean by the winds. So if we imagine a wind blowing steadily across the surface of the ocean. And so this wind is blowing steadily to the north here, I guess. Well, at any parcel of water set in motion to that wind is going to move with the direction of the wind, but it's also going to be deflected rightward in the northern hemisphere, leftward in the southern hemisphere, because of the Coriolis effect. So in an idealized sense, the surface wind, the surface air is blowing, and the surface water starts moving, but it's deflected to the right a little bit. And this deflection is going to be dependent on latitude. So this deflection is going to be greater in the high latitudes and lower in the low latitudes. All right, so this water starts in motion due to the wind, and it's somewhat deflected by the Coriolis effect. Well, this motion is, the motion of this water is translated or transmitted to layers of water deeper in the water column. Okay? So this motion deflected to the right is inducing motion in water parcels deeper in the water column. Well, those motions are also deflected. And so you have this idealized spiral of water motion, okay? And the net effect is that, consider, so, and eventually you get deep enough at about 100 meters depth in this diagram. At about 100 meters depth, there's no longer any effect of the wind, so there's no longer water being set in motion by the movement of water at shallower depths. So if we average out the net motion of water across all of these deflected depths, the net effect is to move water at right angles to the wind. And those right angles are going to be to the right of the wind in the northern hemisphere and to the left of the wind in the southern hemisphere. So here's this hugely important idea, which is that if we set water in motion by having wind move across its surface, the direction of that wind is not going to, the direction of that water that's moving because of the wind is not going to be in the same direction as the wind. It's actually going to be at right angles to the wind. Right angles to the right in the northern hemisphere, at right angles to the right, to the left in the southern hemisphere. So this is what's called an Ekman spiral. Now, I should emphasize that an Ekman spiral is an intellectual concept. You'd be very hard pressed to actually go out in the ocean and measure precisely. It's a theoretical consideration. So you'd be hard pressed to go out and measure the wind blowing and then try to use some kind of a current meter to measure the motion at different depths. In practical terms, that would be an extremely difficult set of measurements to make. However, we can be certain that that's what's happening, because when we look at larger scales at the motion of water induced by wind, we find that this right angle, 90 degree to the right of the wind, is consistent across large scale measurements. Okay. All right, so just to reiterate a little bit, if we have a high, we're going to have an acceleration downward across the gradients. And then there's going to be so gravity is, inducing this deflection here. And then the Coriolis effect is going to be inducing a flow in this direction. So you get around a high in the northern hemisphere, you get a clockwise motion. Well, the same thing would apply if you had a low pressure region. But in the low pressure region, instead of water or air moving away from the high, in a low pressure region, water is going to be coming from the surrounding area and flowing downhill to try to fill that low point. Okay. Well, if it's flowing downhill to fill that low point in the northern hemisphere, it's going to be deflected to the right. Okay, so motion in this direction is going to be deflected to the right. And so that's why around a low pressure region, we tend to get anticyclonic, or actually cyclonic, anti-clockwise motion of air. And so that's why a hurricane, if you look at a hurricane has got a low pressure region. There's air rushing in to fill that. That air is, rising up and heating and rising up very steeply. And there's strong surface winds. Well, those surface winds are going to be deflected to the right of the flow. Well, and since it's flowing towards the center, that's going to produce a anti-clockwise, or what's called cyclonic motion. So anti-clockwise motion. And so that applies whether it's a high pressure region in the ocean, or high pressure region in the atmosphere, or in low pressure region in the ocean and low pressure region in the atmosphere. And you can see this effect. Let's see, I'm going to go back a couple of slides. You can see this effect. I'm not going to go through all the calculations here, but we can see the effect of this Coriolis. Now here we are, we're looking at, this is a satellite image of smoke. This picture was taken during the first Gulf War, and you may not remember during the first Gulf War, but when Saddam Hussein retreated from Kuwait, he set all the oil fields on fire. One of the biggest oil field fires, and also one of the biggest oil spills in history, occurred as a result of the Gulf War. So there was a huge amount of oil got spilled into the ocean here. Well, and there were huge fires, and the fires burned for weeks until they were finally able to put them out. And so these are smoke clouds, which are moving with wind. And in this case, it's a northern wind. It's a wind coming out of the north and blowing to the south. And you can see then that these currents of smoke, or these plumes of smoke, have this deflection, and that deflection is due to this Coriolis effect. Okay. And just as a sort of a matter of historical interest, the first understandings of trying to calculate this Coriolis effect were not performed for sailors or people trying to understand the motion of wind. The reason for trying to understand and figure out the Coriolis effect was for artillery officers trying to calculate where their artillery shells would land. Remember the picture that we showed? We were talking about the paper airplane. Well, the same thing applies if you fire an artillery shell. The artillery shell is going to also be deflected to the right or the left, depending on which hemisphere you're in. If you're trying to hit your enemy with your artillery shell, that little bit of difference is going to be important. And it's also, we can calculate, if we go through this, that the wind speed here is about 20 knots, 10 meters per second, acting over a distance of about 100 kilometers, results in about acceleration for about 10,000 seconds, a deflection of about 30,000 meters, 30 kilometers. So that's approximately what we're doing here. So there's an acceleration to the right of about 0.0003 meters per second squared. Okay, so that's the accelerations here, and we're just working these out from using our principles of vector addition. So the sine of the latitude should be the intensity of the Coriolis effect. So the sine of the latitude times this effect should tell us how much the effect should be. Well, that works out to the kind of Coriolis effect that we get at precisely this latitude, which is about 30 degrees north latitude, roughly the same latitude as we're at here in Florida. So you can use Coriolis. You can observe that the Coriolis effect does work over large scales. Although if you were anywhere in this smoke cloud trying to measure that, you'd have a hard time figuring out what was actually happening. So that's why I say, you know, if you're trying to measure the Ekman spiral directly, you'd have a tough time. But by stepping back and looking at what happens to the large scale movement of water, you can have a better shot at that. All right. Well, that was about as much as I wanted to talk about today. So, you know, this is the trade wind, the direction of water motion, and that's the big message that I want you to take away from today. That we've sort of established how we generate these surface winds with differences in heating of the earth, and then convection cells that are responding to these differences. And then here we're saying, okay, well, what happens if we have a trade wind that's blowing in this direction and we get a deflection to the right? So this water motion, you know, continues clockwise, and this creates these gyre-like effects. And we'll talk more about gyres. Yeah, so, you know, the same concept applies here. You know, you have this wind force, direction of motion, and the deflection and the accelerations get less and less as you get further down in the water column. So the average flow is going to be at right angles to the wind, either right angles to the right in the northern hemisphere or right angles to the left in the southern hemisphere. Okay. And if we apply that at ocean scales, considering, you know, that we have you know, land barriers formed by the more or less north-south alignment of the continents, we can consider that we get these gyres. So there are these gyres in all of the oceans, and they're displaced towards the western edge of basins. And this flow, this general trend is called the western acceleration, western intensification. And this sets in motion surface currents that, you know, we can see in all of the oceans. Okay, so that's the you know, the concepts here, and a lot to hoist on board. You know, considering things as vectors, which are nice intuitive tools for understanding the different forces acting on anything in motion at any particular time, and then the way in which this Coriolis effect produces these kind of counterintuitive results. So we think, oh, the wind is blowing, water should move with the wind. But no, because we have these, you know, the way in which the water and the frictive force of the wind is translated down into the water, and then the influence of the Coriolis effect at different accelerations, we get this right angle deflection. Okay. So, and we'll talk more about other things, vorticity, gyre formation, and look in a lot more detail, specifically about the kinds of surface currents. You know, the result of this is that the currents that flow along the western margins of the ocean basins tend to be warm, deep, strong currents. And an example of that is the Gulf Stream, which is a narrow, warm, deep current which moves, you know, with a tremendous amount of force and directing water from the southern latitude or lower latitudes northward. And then, you know, of course, there's a gyre. You know, the water continues to circulate in this clockwise fashion. But the currents that you have on the eastern side of ocean basins tend to be broad and shallow, and they're typically cold. Why would they be cold? Well, because the water that's in motion is coming from the higher latitudes. So we have strong, deep, intense flows from in the northern hemisphere and in the northern Atlantic, from the south to the north, so warm water going up, and then as the gyre completes its cycle, we get this broad, colder flow on the western side. So the Gulf Stream is this strong current on the western side of the basin, and then the Canary Current is the returning current, which is broad and cold and not as strong. So this sort of general idea, you know, is what dominates the surface currents in all the oceans. And we'll talk a little bit more about that, a lot more about that on Thursday. But I wanted to pause here, give time for questions, and then I will open up the breakout groups, and we'll spend the last portion of today's class with Carrie and me going from team to team and just going through what you're going to submit for your milestone 2 obligation. So any questions? I've covered a bit of material. We'll get more. You've read about it in the chapters, but these are important concepts, and I want to make sure everybody's following along. So any questions? Any questions at all? No questions. Well, how about any general questions about the milestone 2 assignment?
So for our bibliography, is APA fine?
APA is fine. You could also, in the literature, you can also use, many of the journals have different formats. So oceanographic journals will have a particular format, but APA is fine. I'm certainly okay with APA. Carly Ann.
I was wondering if we're able to use like maybe video documentaries for references.
Can you use a video documentary as a reference? So is that something that you would plan to the video? Would you plan to show the video in your PowerPoint presentation?
Yeah, that's something we could do, but I was just wondering, like, as far as like for research and information on our paper, if we're able to use like a
You
documentary.
can, yeah, I'll allow videos, but you have to cite the video, and
Yeah.
it doesn't count as a peer-reviewed publication. Okay,
Right.
so yes, you can cite videos, and so for how to cite a video, it's a little hard to, that's kind of hard to know what the APA or the the bibliographic format for citing a video. You might need to consult with one of the reference librarians to make sure you get it right, but it's certainly permitted.
Okay, thank you.
Okay then, having no other questions, I will stop sharing my screen, and I will open the breakout rooms, and Carrie and I will circulate amongst the different breakout rooms and see how you're all doing. So go ahead, everybody should join the breakout rooms now.
Can I ask a quick question first?
Sure, Joshua.
So I was just looking at the rubric for milestone 2, and it talks about the bibliography when it says I know that the final bibliography is supposed to contain 10 peer-reviewed, 5 like just articles.
Minimum.
Right, minimum. Yeah, right. For milestone 2, do you want all 15 of those now, or is it like just as many as we've found up until this point?
I think you should have been able to find 10 and 5 by this point. With a team of 6 or 7 people, I think you should be able to find that many. So yeah, I would like to see the minimum, that you meet the minimum threshold for this assignment. Yes.
Just making sure. Thanks.
Okay, all right, Carrie, I guess we'll do it the same way we did. So we're talking to the consistent folks. Anybody having trouble getting into their rooms? I see Victoria, Erica, and Farhan. Victoria, do you need help getting into a room? Farhan, do you need help getting into a room?
Yeah, it keeps putting me in 10.
And where are you supposed to be?
11 or 12, I can't remember.
Let's see. Okay, you should go now. Can you join? There you go. And Victoria, where are you supposed to be? Okay. Hello. How you guys doing?
Good, Professor.
So ocean acidification, have you cogitated further on this? Are you getting up to having better ideas about what you're going to do?
Yeah, we're gonna go ahead with the plankton populations and pretty much look at how it's affecting them and then how that's affecting the overall oceanic environment.
Okay, and so are you getting sense of what kind of principles from oceanography that you can use here for your work?
Well, basically just like, again, with like ocean chemistry and like using those specific reactions detailed
Okay,
in the text to kind of like explain how it's working and
okay.
yeah.
Yeah, and then you could also consider not just what's happening in the surface oceans, but also what happens in the deeper oceans. And so there you could look at this calcium carbonate compensation depth issue. You might also consider, the effects of temperature and increasing temperature on that. Ocean circulation and the way in which, why is it that the plankton have to live in the surface waters, right? Why do they have to live in the surface waters? Because that's where the light is. So the motion of surface waters and the penetration of light, those are all factors that, concepts and ideas from principles of oceanography that you should be familiar with when you're talking about your subject there. Okay. And what's your title? Did you come up with a good title?
Well, we don't really have a specific one yet, but I just typed down like ocean acidification impact on plankton populations and the resulting implications on the marine environments. That's just like an overall.
Yeah, that's pretty good. Got nothing wrong with that. A little wordy, but certainly covers where you're at. And then you're doing okay with finding references? Okay. Have you thought about like a summary of where you want to go with the the overall sort of, not the big picture, of what you're going to try to talk about in your project?
I think mainly we've just we're actually like ironing out the details right now on like what parts we're gonna actually discuss, but the acidification process and how that impacts plankton and how the plankton impacts everything else is
Okay.
definitely the bigger picture that we're focusing on.
Okay. Okay. All right. Well, it sounds like you guys are, you have a good topic. I'm pleased that you're thinking about that and you see that, the ways that you can apply these different things. When you start looking at, what the effects are going to be, you might want to look at, the sort of marine community effects. And we'll talk more about sort of nutrient limits on plankton populations and interactions in different communities, food webs in the ocean. Those are all sort of biological oceanographic processes, that are directly related to, your overall topic area. So that's the thing, is to just kind of be aware, when you're reading this source material, what these principles are, so that you come at it with a more informed point of view, and then that you express it in terms of a solid foundation in these principles. Okay. All right. Well, sounds like you're doing good work. I'll leave you to it.
Thank you.
Thank you.
All right.
If I have enough scientific ones, would that be okay if I don't have as many non-scientific ones? Because I know that there's like a minimum of 10 scientific or 15 scientific, and then you add a couple non-scientific.
Yeah, you can definitely have more than that. You probably don't need that full 85 or whatever you said you had
Yeah.
now.
Okay.
This milestone, you said just like a brief summary of what the citations were.
Okay, Maya, do you want to do
Okay.
those too when you do it, or do you want someone else to do those? I mean, I can. I think it just might be easier to have each person do the sources that they found, because those are the ones you looked at. It would be easier for everyone to just summarize their own, like we're doing for the outline, and then I can go in and organize it once everyone's done that.
Okay, sounds good.
Yeah, I think that's a good idea.
Well, hello. I just wanted to drop into your room here and see how you were doing. So you're still working on hazardous materials and the implications of hazardous. Are you going to, as I recall, when we talked last week, you had a couple ideas. You were looking at the Fukushima. Have you sort of focused that or narrowed that down? Where are you at now?
Yeah, I know we were focused on the Fukushima, and I think we were also going to look at the Chernobyl accident.
Oh yeah. Did you see? Have you watched that Netflix special yet?
I have not. I know Mason said last time he watched it, said it was really good.
It's great. Yeah, I think I was telling you last week that yeah, you should definitely see that because they talk about there's a lot of science in there too. We're not overburdened amount of science, but they do look at that, and comparing the way in which, and I'm okay with, looking at the way in which the planners and the hazard managers, responded or didn't respond to, the potential risks of a tsunami and the design there. And that's certainly something that was present in the Chernobyl thing. The Chernobyl accident, as they lay out in the movie, there were sort of fundamental flaws with the reactor design that the Soviets used in all of their nuclear power generation. And, they didn't want to admit that there were these problems. And so that sort of denial kind of entered into the whole thing. And I think there was a certain amount of that. It was certainly with Fukushima. So you could certainly, talk about that and talk about that in terms of, what needs to, what kind of scientific principles planners and managers should employ, because we've kind of come to a place in society where there's these big questions about, do we believe the science or not? Believe in quotes, but do we accept the consequences of what scientific predictions tell us when we're making our plans, when we're assessing hazards and so forth. You might take the lessons of Fukushima and say, do we have similar hazards or exposures in Florida? That would be a way of kind of turning that around. What are the what sort of risks would there be? We probably won't have the same kind of tsunami in Florida as we have, as they had, same kind of risk as they had in Japan. But there are other risks, like hurricanes, for example, which could produce, similar levels of flooding to what they saw during the Fukushima thing. And, what would happen if that kind of flooding occurred in different places. So one of the things, and, you might think about this. So, one of the things about the Gulf Coast is that there's a tremendous number of oil storage facilities that are located right on the coast. That's not so much here in Florida, but certainly in Texas and Louisiana. Houston, for example, the whole sort of port of Houston, there are thousands and thousands of these great big oil storage tanks. Well, if you had a major storm, Hurricane Ike, for example, was a storm that, just barely missed, if it had gone into Galveston Bay instead of where it, a few tens of kilometers to the south where it went ashore, thousands of those oil storage tankers would have been flooded. And that would have produced, a catastrophe in terms of oil spill. So, you might try to in your conclusion or discussion area, get into some of that. Okay. Any questions before I leave you?
I have a question just about what you're looking for specifically in the timeline section. So what would you like that to specifically include?
The timing?
The section for tasks and timeline. I think we kind of
this is
tasks, but we just need help with what the timeline you want to see in that.
Yeah, I want you to look at the due dates, so milestone 3 is coming up. You're going to revise this milestone. so what are your, and then there's going to be presentations. And so just sort of to get a sort of planning sense of when you need to have the different components of this finished so that you have, goals, in the near term that you can make sure that you're heading towards. I'm not trying to like micromanage you in terms of, we got to have this by next Thursday at 6 o'clock, but I just want you to be thinking about, what the different members of the team are going to be contributing and sort of what the the due dates are. Do somebody drop out there?
Thank you.
Okay. That's all, April.
Thank you.
Okay, well, I'm going to move on then. And I'll look forward to seeing your submission. Patrick, do you need to be somewhere?
Yes, I never got moved to my breakout room.
Which group are you in? Which number?
5.
5?
Yes, thank you.
Here are the Aquaholics.
Hi, good afternoon.
Hi,
Hello.
Hello, how's it going?
Good, how are you?
I'm well. So you're still working on ocean energy generation?
Yes, we are.
Okay. I was reading a thing, I don't know, this is not exactly related, but they're saying, oh, the wind turbines froze in Texas, and that's why they're having all of their power outages. There's also, a lot of analysis that says, well, that's really not what happened. There were other areas where, where they went offline. So that, this idea that wind turbines might be unreliable in bad weather is not necessarily proven by the current circumstances, but that's just something I was reading about this morning. So have you gone a little bit farther in figuring out how you're going to focus your presentation?
For the class presentation or just the written?
Yeah,
part?
well, both the presentation and the report. I mean, somebody in the last group I was in, they were asking me, well, what do you want with this timeline? And the idea of the timeline, I'm not trying to micromanage, your activity, but I did want you to think about, okay, what are the different parts that we have to have here, and who's going to be doing them? Which person is responsible for that, and when do those, when does these parts need to be completed in order for the whole project to stay on track? So that's a, that's a component that you want to. You can be as general or as specific as you need to be in that, but I think you're probably better off to be pretty specific and say, okay, well, so-and-so is going to look into ocean thermal energy conversion or tidal energy conversion. And, they need to get their pieces to us by, March 10th or whatever dates are there. So that was kind of what I need. So I see that you're only 4 people. How are you doing in terms of everybody being able to meet?
We've been doing pretty good. Last week at the end of class when we had the time to meet, we got a lot done on the milestone 2.
Okay.
So,
And everybody.
Yeah, and luckily everyone was there at that meeting.
Okay, and so it's, you are having everybody participate, everybody feel like everybody's pulling their weight.
Yes, they are.
Okay. All right then. Well, are there any questions for me? Just want to remember this assignment is due tonight, so hopefully you're all just about ready to turn it in. Okay.
I don't think we have any questions.
All right. Well, good. I'll look forward to what you turn in.
Wait, actually, last time you told us to correct our title just to make it more formal and scientific.
Yes.
So maybe we can just read it over and see if it sounds better.
Yeah, please.
Okay, so our new title is Combating Climate Change, and then there's a colon, and then it says, The motion of the oceans, waves, currents, and tides carries energy that can be controlled and converted into electricity to power the future.
Okay, a little wordy, but that's certainly, why don't you, I like the way you've done that. So why don't you think about like maybe condensing the subtitle there? So it's not quite such a long paragraph of ideas, but
Okay.
I think you're on track there.
All right.
Okay. All right. Well, I'll look forward to see what you turn in.
Thank
So, sea slugs, how are you doing?
Good.
Sluggish?
Try not to.
So you're still working on oil spills?
Yes, we are.
Yes.
Okay, and have you, so I guess we talked about looking at the Deepwater Horizon oil spill. Are you going to focus exclusively on that, or are you going to look at different other ones?
We were planning on looking exclusively, I'm pretty sure.
Okay.
Yeah.
And then you got I sent you the Atlas article, right?
Right.
Yes.
Okay, good. So that should be helpful. And that's cited by a lot of folks. And I think I might also have sent you the article that I wrote with some others for geophysical, geomarine, what is it? JGR, Journal of Geophysical Research. You saw that?
Yes.
Okay. All right. Well, you got any, are you encountering any sort of technical questions or, things that you're not understanding or wondering about in your researches?
I
So
think,
oh, sorry, go ahead.
no, you can go ahead.
A lot of the questions on the milestone are like really similar. Are we just like kind of like, I'm kind of confused about what the difference between each of like the questions is. Like, obviously the abstract will be like an overview of our project, and then is the outline supposed to be like more specifically how it relates to like the key concepts that we're talking about in class?
Yes. That's milestone 3. Hang on.
And then the tasks and timelines, are you like just like, oh, within the next week or whatever, I'm gonna finish looking up?
Well, no, it's sort of like your end point is a written report and a class presentation. Okay. And so what are all the steps that you have to go through between now and then? You've got you've got to write the thing, you've got to outline it, you've got to, just pick out your figures, make sure your bibliography is in shape. Different team members will be investigating different aspects of the problem. So, Catherine, you're going to look at, the chemical nature of the oil, and Hannah, you want to look at the effects on marine organisms, and Tyler, you will maybe want to look at the engineering that they had to go through to try to control the oil, or why there was a spill in the first place. So there are different, parts of this that you're going to be evaluating, who's going to be doing them, and what sort of schedule do you need to keep to in order to make sure that you get everything done in time.
Okay.
Okay. And bibliography, so that's the task and the timeline. And then, whatever, when you turn it in, we're going to look at it, and hopefully it'll be perfect the first time and you won't need to reserve it. But it may be that it will come back with specific criticisms and we'll say, well, fix this. You need to be more specific about that, and you'll get a chance to revise that. So you should be able to get that full 15 points, assuming that you do everything that we ask in your revision.
All right, awesome. Thank you.
Okay. You.
Here, I can do it. To put into MLA, right?
APA.
APA.
Mhm.
Here, I can do it. It's tools, citations on the Google Doc, and it makes it a lot easier.
Honestly, I was gonna say I'm used to doing MLA anyways, so I don't know. I don't know how many of us care that much.
I don't care. I just had to write an APA paper, so I don't mind keeping the APA trend.
I'll tell you that Word has tools for formatting bibliographies and stuff.
Yeah, within Google Docs.
Yeah, Google Docs. I don't know about, I haven't used the Google Docs tools. There are a lot of different tools. EndNote is something that's available. ProCite is another one. You know, I would like to have time to be able to, you know, explain about using these bibliographic tools because they're really very, very helpful as you start doing your writing. You know, as you become professionals, you'll have more writing to do, and citation is an important part of every writing. So I'd like to have time to do that, but I kind of got to leave it up to everybody because you have different, you know, different software available and different preferences. But the idea of using a bibliographic software will really save you a lot of work, and it'll keep you, you know, make sure that you provide accurate information about your bibliography. So you guys are still working on aquaculture?
Yeah.
And have you, after we talked last week, have you focused or changed direction at all, or sort of, can you like give me an update on where you're at?
Since that other team was working on specifically like, was it oysters?
Uh-huh.
Doing specifically like fish.
Okay.
Yeah.
Yeah, we're just trying to like figure out the scope and go more in depth, and we're breaking up our research topics and like trying to structure the paper really well, like through the introduction through conclusion.
Uh-huh.
And working on our sources right now. And we just have one team member that we haven't really heard of.
Oh yeah.
Yeah, Nelson has not. He hasn't said anything in the chat, or even I don't think he's even been on the doc we're on right now for like the past week.
Oh really? Okay, so that would be.
And I don't even think he's here. Like he missed the past 2 classes, I think.
Okay, what's his name?
The
I want to, you know, I'm not gonna like, you know, I just want to make sure that people don't get too far behind.
Yeah. Nelson Mesnard, I think.
Okay. All right. Well, I will. I'll send him an email and ask him to check in with you. But everybody else is pulling together. You feel like you got a good team. You're enjoying working together.
Mm-hmm.
Yeah,
definitely.
Okay. All right. Well, I will communicate with Nelson and tell him that he's been missed in his group and that he needs to check in with me, and then make sure that he gets with you. And it, you know, maybe sometimes people drop, you know, for various reasons, and then there people have had health issues, and so if it's something like that, I'll let you know. Otherwise, hopefully you'll check back in and be able to contribute to the team.
Okay, thank you.
Okay. All right. So everything is due tonight. So hopefully we'll see your nice milestone, and then whatever revisions we have to do, you'll get the final 15 points based on how it all looks.
Okay.
And this idea of using principles of oceanography, taking these, you know, abstract theoretical concepts and finding real world examples of them, you know, that's certainly something that you can do in, you know, in your topic, because you're looking at food chains and, you know, sort of what the requirements for keeping fish alive are, and you know, sort of unexpected effects, like, you know, there's genuine pollution problems around aquaculture because of the waste from the fish, and you know, that's depending on where these aquaculture facilities are located, you can have different effects. So like, you know, this big Norwegian salmon farming, for example, that's a big deal in Norway. Well, they have a really strong tides, and so they can put these farms, and then the tidal currents tend to move all of the waste offshore, and so you know, those kind of conditions are favorable, or you know, you don't have the same sort of eutrophication, the same sort of contamination, because the water is constantly replenishing. But if you were in an area that had different kind of tides, like in the Gulf of Mexico, for example, where there's much less of a tidal flow, you know, then that could be an issue. Same thing with temperature. Same thing with the supply of where you're going to get the feed for the aquaculture species. And so those are all areas where you can look into the principles that you're thinking about and find applications in the real world. Okay. All right, folks. Well, I will go on then. And
could I ask you one more question?
Of course.
So there's an overarching theme section and the tasks and timeline section. And for the overarching theme section, like, could we structure it like we have like separate, like, introduction, and then the themes that will be in there, and then like materials and methods, and then themes that will be like talked about in there, like that kind of thing?
Sure, you can do it that way.
Yeah.
Yeah, I mean, exactly the way that you're thinking about this, how should I organize this? I'm not going to micromanage and say it has to be exactly this, but you're doing exactly what you should do, Joshua. You're thinking about, okay, these are the different points I've got to cover. How can we put this together in a cohesive way that meets the requirements, but also adapts to the particular topic area that the team is researching.
Okay.
Okay, good job. You're all by yourself.
I am all by myself.
Where's your team?
No one else from my group is here, so I'm just working on milestone 2.
Okay. Have you been? How's the team been working? Have you not been meeting
We
together?
work well. We have a group chat. We're pretty active in there. This is the first time that I've been the only one, so we are fine, and it's mostly done.
Okay.
So it's okay. It was just weird that it was like just me. Someone else was here, but he left because he had a doctor's appointment.
Okay.
Yeah.
Well, are they at least gonna buy you lunch or something for picking up the slack for them?
Hope so.
So too. All right. Okay. Well, I will send a little message to your team from the homepage, from your team homepage, saying, "Hey, I was disappointed that Sage was all by herself. You guys need to support her a little bit better." So maybe that'll make sure that they know that I'm checking up on them.
Okay.
Okay. You have any questions? You're still working on living marine resources?
Yes, we're we're like focusing on the Great Barrier Reef.
Oh, okay.
Climate change is sort of affecting.
All right. You're finding good material there?
We are actually. There's quite a bit. So we're trying to narrow it down to the more specific ones, and doing pretty well at that. So
Okay.
Yeah.
All right. Well, sorry that you're by yourself. It's usually better. Do you have any questions about stuff that's come up, or?
I don't think so. I think we're pretty much good.
Okay.
If anyone else, I don't know if anyone else has any questions because they're not here.
Well, they're not here to ask them. So.
Questions.
Okay. All right. Okay then. Well, I'm going to end the breakout rooms now. We'll get all together. So hopefully we'll have a chance to see your product.
Yes.
Well, I guess we're pretty well done today. Any questions come up for anything that you have. Otherwise, do your reading quiz. It's been posted online, and the material is all in the Garrison textbook, so that should be no problem. And if you have any questions about anything, of course, you can always email me. I'll say again, if you send a email to me, two things. Make sure that you put OCE 4008 in the subject line, and also copy Carrie O'Reilly, because both of us, sometimes she'll respond or sometimes I'll respond, but you're much more likely to get a prompt response if you copy both me and Carrie at the same time. Okay, so just those two things. Put OCE 4008 in the subject line, along with whatever your question is, and then copy Carrie O'Reilly as well as myself. Okay, I guess that's pretty much all for today. Are there any questions before we zoom away? No? Everybody doing okay? All right then, so we'll look for your submissions for milestone 2 by midnight tonight. I'll post the video of today's class on the YouTube site that you're looking at regularly. And I'll expect we'll meet again on Thursday and finish the covering the material that's in the ocean circulation chapter. All righty, goodbye everybody.
Bye, thank you.
Thank you.